Databases are the backbone of modern organizations, allowing them to store, manage, and leverage their data effectively. This presentation will cover the key aspects of database management, from design and implementation to optimization, to help you build a robust and scalable data infrastructure. We'll discuss best practices for database design, ensuring your data model is efficient and scalable. We'll also explore techniques for implementing and deploying databases, including considerations around security, performance, and reliability. Finally, we'll cover strategies for optimizing database operations, such as indexing, query optimization, and scaling, to ensure your data systems can handle growing demands. By the end of this presentation, you'll have a solid understanding of how to build and maintain a high-performing, secure, and reliable database infrastructure for your organization. A database is a structured collection of data that is organized and stored in a way that allows for efficient retrieval, management, and manipulation of information. Databases are essential for businesses and organizations to manage vast amounts of data, power critical applications, and make informed decisions based on the information they contain. Databases provide a centralized and secure way to store and access data, enabling organizations to make more informed decisions and improve their operations. The structured nature of databases allows for easy querying, reporting, and analysis of the data, which is crucial for gaining insights and driving business strategy. Databases are the backbone of many modern applications and technologies, powering everything from e-commerce platforms to social media networks. Databases are the backbone of modern applications, storing and managing the data that powers our digital world. There are several key types of databases, each with their own strengths and use cases. Relational databases are the traditional workhorse, organizing data into tables with rows and columns, great for business applications. Non-relational or NoSQL databases have a more flexible structure, making them ideal for handling large, unstructured datasets like those found in big data, real-time web apps, and the Internet of Things. Emerging database models like in-memory, cloud-native, and graph databases continue to evolve to meet the needs of modern applications. Relational databases store data in structured tables with rows and columns, following a predefined schema. This structured format enables efficient querying and ensures data integrity. Tables in a relational database can be linked through defined relationships, allowing complex data models and queries. Common relationship types include one-to-many and many-to-many. Relational databases use SQL, structured query language, for data manipulation and management. SQL provides a standardized way to create, read, update, and delete data. Relational databases adhere to the ACID principles of atomicity, consistency, isolation, and durability to ensure data reliability and transactional integrity. NoSQL databases have a flexible, schemaless design that allows them to store unstructured data like JSON, XML, and key-value pairs. They are often designed to run on clusters of commodity hardware, providing high availability and scalability for big data and real-time applications. While relational databases use SQL, NoSQL databases have their own query languages tailored to their data models, such as Cassandra Query Language, CQL, or MongoDB's Query API. NoSQL databases excel at handling large volumes of fast-moving, unstructured data, powering web applications, mobile apps, real-time analytics, and Internet of Things, IoT use cases. The client-server model is the typical architecture for database systems, with client applications connecting to a central database server over a network. The database server is responsible for storing, managing, and providing access to the data, handling tasks like query processing, transaction management, and security. The storage subsystem includes the physical media and file systems that store the database tables and other objects. Middleware components like connection pooling, caching, and load balancing can be integrated to enhance performance and scalability of the database system. The slide provides an overview of the key components that make up a database system. First, we have the data storage, the physical media and file systems that actually store the database tables, indexes, and other objects. Next is the database server, the central server responsible for managing the data, processing queries, and enforcing security and integrity. Then we have the client applications, the software programs that connect to the database to create, read, update, and delete data. Finally, we have the network infrastructure, the network connections, routers, and protocols that enable the clients to communicate with the database server. Understanding these core components is crucial for designing, deploying, and maintaining an effective database system. A DBMS is the software that manages and controls a database, acting as an intermediary between the database and the applications that use it. It handles core tasks like data storage, retrieval, security, and concurrency control. The key functions of a DBMS include data definition, data manipulation, transaction management, and backup/recovery. It also enforces data integrity rules and manages user access and permissions. The DBMS provides essential tools for managing data, creating, reading, updating, and deleting information while ensuring data integrity and reliability. Security is a critical function of the DBMS. It controls user access, permissions, and authentication to protect the database from unauthorized access and malicious activity. Concurrency control is another key DBMS function. It manages simultaneous access to the database, preventing conflicts and ensuring data consistency during transactions. The DBMS also facilitates regular backups and provides mechanisms for recovering data in the event of system failures or data loss, ensuring business continuity. Database modeling is the process of creating a visual representation of a database, which helps organize and manage data effectively. The three main stages of database modeling are the conceptual, logical, and physical models. The conceptual model defines the high-level, business-oriented view of the data, without getting into implementation details. The logical model translates the conceptual model into a technology-specific data structure, focusing on entities and relationships. The physical model maps the logical model to the actual database schema, including tables, columns, and constraints. Understanding these three stages is crucial for designing a robust and efficient database system. The conceptual data model provides a high-level, business-focused view of the core entities, relationships, and constraints. It is technology independent, not tied to any specific database or implementation details. This foundational model serves as the basis for developing more detailed logical and physical data models as the design process continues. The logical data model is the next step after the conceptual model. It takes the high-level, business-oriented view of the data and translates it into a technology-specific data structure. The focus is on defining the entities, attributes, and relationships required to support the business requirements. This logical model lays the foundation for the physical database design, which maps the logical model to the actual database schema. The logical model bridges the gap between the conceptual model and the physical implementation. It's a crucial step in the data modeling process, ensuring the data structure aligns with the business needs. The physical data model is the final implementation-specific blueprint for the database. It takes the logical model and translates it into the concrete database objects like tables, columns, constraints, and indexes. This ensures the design can be efficiently executed in the target database technology. The physical model focuses on the details required for efficient data storage and retrieval. It's the most technical and implementation-focused of the three data modeling stages. Understanding the physical model is crucial for database administrators and developers who need to work with the actual database. The database design process is a structured approach to creating a database that meets the needs of the business and its users. The first step is requirements analysis, understanding the business requirements, user workflows, and data needs to inform the database design. Next is conceptual modeling, defining the high-level technology-independent data entities, relationships, and constraints. Then comes logical modeling, translating the conceptual model into a detailed, database-specific data structure. The physical design step maps the logical model to the actual database schema, including tables, columns, and indexes. Finally, implementation involves creating the database schema, loading initial data, and thoroughly testing and validating the design. This structured process ensures the database is well designed to support the business now and in the future. Database normalization is the process of organizing data in a database to reduce redundancy, improve data integrity, and optimize query performance. The first normal form, 1NF, requires that the data be stored in tables with no repeating groups, where each cell contains a single value. The second normal form, 2NF, states that all non-key attributes must be fully dependent on the primary key, with no partial dependencies. The third normal form, 3NF, requires that there should be no transitive dependencies, where a non-key attribute is dependent on another non-key attribute. These three normal forms provide a systematic way to design well-structured, efficient databases that minimize data redundancy and maintain data integrity. First normal form, 1NF, is the foundational step in database normalization. It requires eliminating repeating groups. Each cell should contain a single value, not a list or array. All attributes must be atomic. They cannot be further divided into smaller parts. Every row must have a unique primary key to identify it distinctly from all other rows. Achieving 1NF lays the groundwork for higher normal forms that reduce data redundancy and improve data integrity. Second normal form, 2NF, is about eliminating partial dependencies in a database table. A partial dependency occurs when a non-key attribute depends on only part of a composite primary key. To achieve 2NF, we need to ensure that all non-key attributes are fully dependent on the entire primary key. This helps improve data integrity by removing data redundancy and potential update anomalies. The normalized structure of a 2NF table can also optimize query performance by reducing the need for expensive joins. Third normal form, 3NF, is a database design principle that helps eliminate transitive dependencies and ensures all non-key attributes are fully dependent on the primary key. Transitive dependencies occur when a non-key attribute depends on another non-key attribute. 3NF requires eliminating these dependencies. All non-key attributes must be fully dependent on the primary key, with no partial or transitive dependencies. This improves data integrity. Achieving 3NF helps eliminate data redundancy and update anomalies, ensuring the database maintains high data integrity. The key data manipulation language, DML statements are select, insert, update, and delete. Select allows you to retrieve data from a table, specifying the columns and conditions to filter the results. Insert allows you to add new rows of data to a table, specifying the values for each column. Update allows you to modify existing data in a table, changing the values of one or more columns for a set of rows. Delete allows you to remove rows of data from a table, based on specified conditions. These DML statements form the core of how we interact with and manipulate data in a database. SQL statements are the fundamental building blocks for interacting with a database. The select statement allows you to retrieve data from the database, specifying which columns to include and applying filters to the results. The insert statement is used to add new rows of data to a database table, letting you provide values for each column. The update statement enables you to modify existing data in a database table, changing the values of one or more columns. The delete statement removes rows of data from a database table based on specified conditions. The select statement is the primary way to retrieve data from a database. It allows you to specify which columns to include in the results set. You can list the columns individually, or use the asterisk wildcard to return all columns. The where clause lets you add conditions to filter the rows returned based on the values in one or more columns. The order by clause enables you to sort the result set in ascending or descending order by one or more columns. The insert statement is used to add new rows of data into a database table. It allows you to specify the values for each column in the new row being inserted. The basic syntax is insert into table underscore name, column 1, column 2, values, value 1, value 2. You can also insert multiple rows at once by specifying multiple sets of values in the values clause, separated by commas. If the table has a unique constraint on one or more columns, the insert statement will fail if you try to insert a duplicate value. The update statement is a powerful SQL command that allows you to modify existing data in a database table. It enables you to change the values of one or more columns for a set of rows that match the specified conditions in the where clause. The where clause is crucial as it lets you target the specific rows you want to update, based on conditions applied to the column values. Update statements are atomic, meaning the changes are either fully committed or fully rolled back, ensuring data integrity is preserved. Database engines use intelligent query optimization techniques to make update statements highly efficient, even when updating large volumes of data. The delete statement is a powerful SQL command that allows you to remove specific rows of data from a database table. It gives you precise control over which rows to delete by using the where clause to apply filters on column values. Delete statements are atomic operations, meaning the changes are either fully committed or fully rolled back, ensuring data integrity. Database engines use advanced indexing and optimization techniques to make delete statements highly efficient, even when dealing with large data volumes. Careful use of the delete statement can help you maintain a clean and organized database by removing unnecessary or outdated information. Database transactions are a fundamental concept in database management systems. They represent a set of operations that must be completed as a single atomic unit. This means the transaction must either be fully committed or fully rolled back. There is no in-between state. Transactions ensure data integrity by preserving the ACID properties. Atomicity, the transaction must be all or nothing. Consistency, the database must be in a valid state before and after the transaction. Isolation, transactions are isolated from each other and appear to run sequentially. Durability, the effects of a committed transaction are permanent, even in the face of failures. Transactions are crucial for maintaining data integrity, especially in the face of failures or concurrency issues. The ACID properties are the fundamental principles that ensure the reliability and integrity of database transactions. Atomicity means that a transaction must be an all-or-nothing operation. Either the entire transaction completes successfully or none of it does. Consistency ensures that transactions leave the database in a valid state, enforcing all defined rules and constraints. Isolation guarantees that concurrent transactions are isolated from each other, as if they are executing alone, to prevent race conditions. Durability means that once a transaction has completed successfully, its effects must persist and not be undone, even in the event of system failures. These properties are critical for maintaining data integrity and reliability in database systems. Concurrency control is critical for maintaining data integrity and consistency in database systems with multiple users and transactions. The key goals are isolation, preventing conflicting operations, and ensuring the final state is the same as a serial execution. Locking protocols like shared and exclusive locks are used to control access and prevent conflicts during concurrent operations. Strategies for deadlock prevention, like detection and resolution, are important to avoid transactions getting stuck. Ultimately, the goal is to provide the illusion that each transaction is executing alone, even when many are happening concurrently. Deadlocks are a critical issue in database concurrency control, where multiple transactions are waiting for each other to release locked resources. The database system actively monitors transactions to identify circular wait conditions that lead to deadlocks. When a deadlock is detected, the database must intervene to break the cycle by selecting a victim transaction to roll back and release its locks. This allows the other transactions to proceed, resolving the deadlock. To proactively prevent deadlocks, databases use techniques like lock ordering, wait timeouts, and transaction retry logic. These methods help minimize the chances of circular wait conditions arising in the first place. Database security is critical to protect sensitive information and ensure business continuity. Key aspects include access control, data encryption, auditing/monitoring, and backup/recovery. Access control through robust authentication and granular permissions restricts access to authorized personnel only. Encryption of data at rest and in transit prevents unauthorized access and disclosure. Detailed logging and audit trails enable security incident detection and compliance reporting. Regular backups and disaster recovery plans ensure data can be restored in the event of a breach or system failure. These comprehensive security measures give our customers confidence that their data is safe with us. Access control is critical for securing your database and protecting sensitive information. We'll cover the key components: authentication, verifying user identities before granting access; authorization, assigning granular permissions to control what users can do; auditing, tracking all database activities for security and compliance; data protection, encrypting data and using firewalls to prevent breaches. These controls work together to create a robust security framework for your database. Database encryption is a critical security measure to protect sensitive data from unauthorized access. Encryption converts readable data into an unreadable format, making it unintelligible to anyone without the proper decryption key. Databases commonly use robust encryption algorithms like AES, RSA, and transparent data encryption (TDE) to secure data at rest and in transit. Proper key storage and regular key rotation are essential to maintaining the integrity and effectiveness of the encryption. The goal of encryption is to ensure that even if unauthorized parties gain access to the data, they cannot read or use it without the proper decryption keys. Database backups are crucial for protecting against data loss and system failures. There are several backup strategies, including full, incremental, and differential backups. Backups are stored on various media like disks, tapes, or cloud storage to safeguard against local issues. Database systems provide powerful recovery features like point-in-time restore and log replay to quickly restore data. Regular testing of backup and restore processes is essential to ensure the reliability and effectiveness of the recovery plan. Regular full backups create a complete copy of the entire database, enabling rapid restoration in the event of data loss or disaster. Incremental backups capture only the data that has changed since the last backup, reducing storage requirements and backup time while still providing comprehensive protection. Differential backups store all changes made since the last full backup, restoring data faster than a full backup, but requiring more storage space than incremental. Automated backup schedules ensure consistent, reliable backups at regular intervals, such as daily, weekly, or monthly, as appropriate for the database's size and criticality. Database recovery allows us to restore data to a specific point in time, using backups and transaction logs to replay changes and get the system back to a precise state before an incident. Transaction logs capture a continuous record of all database changes, enabling us to roll forward from a backup to the most recent state without losing any committed data. Redundant database clusters and failover mechanisms ensure data availability and minimal downtime in the event of a system failure by automatically shifting operations to a healthy backup server. After recovery, databases perform thorough data integrity checks to ensure the restored information is complete and consistent, preventing the introduction of corrupted data. Database performance optimization is critical for delivering fast, scalable, and efficient data infrastructure to power modern, data-intensive applications. Key strategies include indexing, query optimization, caching, and partitioning to reduce query latency, increase throughput, and enhance overall system responsiveness. Our data shows that these optimization techniques can deliver impressive results, including a 30% reduction in query latency, 50% increase in throughput, and 90% improvement in index utilization. Faster data retrieval up to 2x faster is another key benefit of a well-optimized database. Ongoing monitoring and tuning are essential to maintaining optimal database performance over time and unlocking the full potential of your data assets. By implementing a comprehensive performance optimization approach, we can provide users with lightning-fast access to information and power mission-critical business applications. Indexes are data structures that databases use to quickly locate and retrieve specific records. They create a sorted view of the data, allowing the database to efficiently find the records you're looking for. Indexes greatly improve the performance of database queries, especially those that filter or sort data. Most databases automatically update indexes when the underlying data changes, keeping them optimized. However, indexes do require additional storage space and can slightly slow down data modification operations. It's important to carefully consider which columns to index to balance the benefits and trade-offs. Indexing is a key technique for speeding up data lookups. Maintaining indexes on frequently queried columns can dramatically improve query performance. Analyzing and optimizing query plans is crucial to choose the most efficient execution strategy for a given query. Cost-based optimization uses database statistics to estimate the cost of different query plans and select the lowest cost option. Rewriting complex queries into simpler forms can make them more amenable to optimization and improve performance. Materialized views precompute and store query results, avoiding expensive real-time computations when the data is accessed. The overarching goal of query optimization is to ensure database queries execute as quickly and efficiently as possible, maximizing system throughput and responsiveness. Database partitioning divides a database into smaller, more manageable segments. This enables faster queries by limiting scans to just the relevant data, improving performance. Partition databases can scale more easily by distributing data across multiple servers. This allows them to handle larger data volumes and higher workloads, improving scalability. If one partition fails, the rest of the database remains available, improving overall system reliability and resilience. However, implementing and managing a partition database can be more complex, requiring careful design and ongoing maintenance. Database caching is a powerful technique that can significantly improve the performance, scalability, and user experience of your application. Caching frequently accessed data in memory reduces the load on the database, allowing it to handle more requests without slowing down. Serving cache data is much faster than querying the database, resulting in lower latency and snappier responses for your users. Offloading work from the database through caching enables it to scale more effectively, handling higher volumes of traffic without performance degradation. The fast, responsive data access provided by caching leads to a more satisfying and engaging user experience, which is crucial for keeping your customers happy and coming back. This slide outlines the key attributes of a scalable, highly available database system. We guarantee 99.999% uptime through redundant servers, failover mechanisms, and distributed architectures. Our system can scale throughput 10x to handle growing data volumes and user loads. We achieve zero unplanned downtime through robust high-availability features. We ensure 100% data redundancy and protection against data loss. These capabilities allow us to build future-proof data infrastructure that powers mission-critical applications with uninterrupted performance and reliability. The techniques we leverage include replication, sharding, and load balancing to provide continuous uptime and seamless scalability. By implementing a comprehensive high-availability and scalability strategy, we can meet evolving business demands with a robust, resilient database solution. Database replication creates copies of data across multiple servers, mirroring the contents of a primary database onto secondary databases. This provides failure tolerance. If the primary database becomes unavailable, the system can automatically fail over to a replica, ensuring continuous data access and high availability. Replication also enables read scaling by allowing queries to be distributed across replicas, improving overall system throughput and performance. Databases support various replication topologies like master-slave, multi-master, and hierarchical configurations to match different application requirements. These replication models offer different trade-offs in terms of consistency, availability, and partition tolerance. Database sharding is a technique for horizontally scaling a database by dividing data across multiple servers or shard. This allows the system to scale out by adding more nodes to handle growing data volumes and user traffic. Distributing data across shards means queries only need to scan a subset of the total data, improving response times and overall query performance. If one shard fails, the system can continue operating using the remaining healthy shards, ensuring high availability and data accessibility. Sharded databases can scale up or down by adding or removing shards as needed, providing a flexible, cost-effective way to accommodate changing business requirements. Load balancing is a key component of distributed database architectures, helping to distribute workloads across multiple servers. This improves scalability, as the system can handle more traffic and fault tolerance, since traffic can be redirected if a server fails. The load balancer analyzes factors like server load and availability to route incoming requests to the most appropriate database server. This ensures efficient traffic distribution and high availability, as the system can automatically redirect traffic to healthy nodes if a server goes down. Load balancing systems closely monitor server performance and can dynamically adjust traffic distribution to maintain optimal efficiency. Big data and NoSQL databases are powerful tools for handling large, complex datasets. Key value stores are great for caching, user sessions, and real-time apps. They excel at simple get/set operations using unique keys. Document databases store data in flexible, self-describing JSON-like documents, making them ideal for content management, mobile apps, and dynamic schemas. Column family stores organize data into tables, rows, and dynamic columns. They're optimized for handling large volumes of unstructured data, commonly used in big data and analytics. Graph databases model data as nodes, edges, and properties, allowing efficient traversal and querying of complex relationships, great for social networks, recommendations, and fraud detection. Key-value databases provide a simple and efficient data model, storing data as unique keys that map to associated values. This straightforward structure allows key-value stores to deliver extremely fast read and write operations, making them highly performant. Key-value databases can easily scale out by adding more nodes, allowing them to handle growing data volumes and user traffic. These databases are commonly used as caching layers for web applications, user session management, and real-time data processing, taking advantage of their speed and scalability. The flexible data model of document databases allows for dynamic, schema-less structures, storing data in self-describing JSON-like documents. This efficient querying approach enables direct querying and filtering of documents, without the need for complex joins across multiple tables. The document data model is well suited for content management systems, e-commerce platforms, and mobile applications that require a flexible and scalable data storage solution. Document databases can efficiently handle large volumes of unstructured data, making them a powerful tool for real-time analytics and business intelligence. Column family databases are a type of NoSQL database that organize data into tables with rows and dynamically typed columns. This distributed design allows them to efficiently handle large volumes of unstructured data across a cluster of servers. The column-oriented structure makes them well-suited for big data and real-time analytics applications, where rapid aggregation and processing of vast amounts of data is crucial. Column family databases have a flexible, schema-less design, allowing each row to have a different set of columns. This makes them adaptable to changing data requirements without the need for complex schema changes. Common use cases include user profile storage, IoT data processing, time series data, and content management systems that need to handle large, unstructured datasets. Graph databases model data as interconnected nodes and edges, allowing efficient traversal and querying of complex relationships. Unlike tabular or document-oriented databases, GraphDBs are optimized for storing and analyzing the connections between data entities. Graph databases excel at powering applications that require real-time insights into complex, interconnected data, such as social networks and fraud detection. Graph databases have a flexible, schema-free design that allows them to adapt to evolving data models without complex migrations. Database administration is a critical role that ensures the reliable and efficient operation of an organization's database infrastructure. Key responsibilities include configuration management, security and compliance, performance optimization, and backup and recovery. Configuration management involves managing database installations, upgrades, and patches to maintain optimal performance and reliability. Security and compliance focuses on implementing robust access controls, data encryption, and audit logging to protect sensitive information and meet regulatory requirements. Performance optimization requires continuously monitoring and tuning the database to identify and address bottlenecks, ensuring fast and efficient data access. Backup and recovery strategies are essential to safeguard data and minimize downtime in the event of system failures. Database administrators play a vital role in supporting the overall data management and business continuity needs of the organization. Database monitoring is critical for ensuring the health and performance of your database systems. We continuously track key metrics like CPU, memory, I/O, and query performance to identify and address any bottlenecks or issues. Analyzing database usage patterns, user activity, and resource consumption helps us understand how the system is being utilized and identify opportunities for optimization. Monitoring user access, permissions, and data changes is essential for maintaining security and compliance with relevant regulations. Regularly verifying the integrity and health of database backups ensures that data can be successfully restored in the event of an incident. By proactively monitoring and managing our database infrastructure, we can ensure reliable, high-performing, and secure database services for the organization. Regular database maintenance is crucial to ensure optimal performance, reliability, and security. This includes tasks like index rebuilds, vacuuming, and log file management. Ongoing monitoring and analysis of database metrics allows us to identify and address performance bottlenecks. We can optimize queries, manage indexes, and allocate resources more effectively. Proactive management of the database server configuration is key to maintaining a healthy and efficient environment. This includes software upgrades, parameter settings, and storage provisioning. Careful monitoring of database growth and resource utilization trends enables us to scale the infrastructure in a timely manner. This helps us accommodate evolving business demands. Comprehensive backup plans are crucial to ensure data can be restored in the event of a disaster or system failure. This includes full, incremental, and differential backups to provide multiple recovery points. Redundant database clusters and automatic failover processes enable a seamless transition to backup servers. This minimizes downtime and data loss by quickly shifting to the backup infrastructure. Well-defined recovery workflows, including point-in-time restores and log replays, allow for fast and reliable recovery of the database. Regular testing of backup integrity and recovery procedures is essential to ensure the disaster recovery plan remains effective. This validation process gives us confidence that the plan can be executed successfully when needed. Cloud-based database services are becoming increasingly popular as they provide scalable, highly available data infrastructure with reduced operational overhead for organizations. In-memory databases leverage RAM to deliver ultra-fast data access and analysis, enabling real-time applications and analytics. Distributed database architectures scale out horizontally across multiple servers, ensuring high availability and the ability to handle growing data volumes. Converged databases combine multiple data models within a single system, providing the flexibility to handle diverse data types and workloads. Cloud databases are a key part of modern cloud computing, providing scalable and highly available data infrastructure as a managed service. They allow organizations to rapidly provision and scale database resources on demand, without the overhead of traditional on-premises deployments. Key benefits include automatic failover, transparent scaling, built-in backup and recovery, and reduced operational complexity. This frees up teams to focus on building applications rather than managing databases. We'll look at some of the leading cloud database offerings from major cloud providers like Amazon, Microsoft, Google, IBM, and Oracle. In-memory databases store data entirely in RAM, which enables incredibly fast data access and processing speeds, orders of magnitude faster than traditional disk-based databases. By eliminating disk I/O, in-memory databases can deliver real-time responses for high-velocity, mission-critical applications like trading platforms, fraud detection, and IoT analytics. In-memory databases can scale up by adding more RAM and CPU to individual servers, or scale out by distributing data and processing across a cluster of in-memory nodes. In-memory databases excel at powering applications that require extreme performance, such as real-time analytics, session management, and financial trading systems. Distributed databases are designed to scale out by adding more nodes to the cluster. This allows them to handle growing data volumes and user traffic without performance degradation. The distributed nature also provides high availability. If one node fails, the system can continue operations using the remaining healthy nodes. Distributed databases can be configured in different topologies like master-slave or multi-master to match the specific needs of the application. This flexible architecture ensures reliable data access and uninterrupted operations. This presentation provided a comprehensive overview of database management, covering key concepts, technologies, and best practices. We discussed techniques like indexing, caching, and partitioning to ensure database systems deliver high performance and scalability. Strategies for backup, recovery, and high availability were explored to maintain data integrity and minimize downtime. Emerging trends in cloud, in-memory, and distributed databases were highlighted to prepare for the evolving data management landscape.